All right, if anybody hasn't said anything in the chat, please say that you're here. That looks to be pretty much everybody. Share this. Yeah, there's 13 on Zoom, 6 of you guys here. So that means roughly 3 people.
This is the one class I feel like
I feel that way too, but apparently an awful lot of your peers do not. So it is what it is. All right. Today we are going to be developing our high frequency models for our transistors. Let's get cracking. All right. Yeah, I'm doing it in an order that makes sense to me because I hate your textbook. So yeah, I think this would be, I think what we're going to be covering today is all of section 11.2, I think, where we jumped over a couple of things at the beginning that we will touch upon when we actually get into the circuit analysis a bit. Specifically, we jumped over estimating poles and zeros and all that kind of jazz, and we'll cover that momentarily once we figure out why the hell it's important. All right, so we're going to first start with our BJT model. And I'm going to start by drawing it. So, and then we're going to talk about where all this different stuff comes from. So our high frequency, small signal BJT model is going to look something like this. So we have our regular R pi and V pi between our base and our emitter. And we're going to have an additional component now, which I'm going to call C pi. We'll talk about where that comes from. We're going to have a capacitor C mu between our collector and our base. Here we have good old GM V pi as per usual. So I'm going to call this node my emitter. We have our early effect resistance R naught. And then between the collector and ground, we have a capacitance CCS. And then here is our collector node. So we have modified our small signal BJT model with 3 capacitances, okay? And to understand why we have these capacitances, it's necessary to look at a cross section of a BJT during forward active operation. So give me just a moment and we'll draw that guy real quick. Here we have our emitter terminal. Here is our collector terminal. Here is our base terminal in forward active operation. We have a voltage VBE greater than 0, which is forward biasing the base emitter junction. Actually, I got that backwards. The emitter is the one that's really heavily doped, and the collector is the one that's most lightly doped. I apologize for that. We also have some collector base voltage, which I will call CBE. And this quantity, or excuse me, VB, goodness gracious, VCB. And this quantity is also greater than 0. So it is reverse biasing the collector base junction, okay? So since we have two PN junctions, I'm going to go ahead and specify a couple of things. I think I did electrons as red in 335. So we're going to have a depletion region between our base emitter junction and our collector base junction. Where we have some amount of charge stored here. So I'm going to call this QBEP. The charge stored in this region is QBEN. The charge stored here, we'll call it QCBN. And the charge here, we'll call QCBP. In addition to these depletion regions, which are going to form some of our capacitances, we are also going to have what's called a diffusion capacitance, which I know that I talked to my section about in 335, but I'm not entirely sure that it was covered in Dr. Batari's section. So we'll take just a moment to figure out what that is or describe that. So this red horizontal lines are representing my electron density, so a number of electrons per cubic centimeter. Because our base emitter junction is forward biased, that means that that space charge layer is very small, and so the probability of electrons diffusing from the emitter to the base is high. So we should see a profile that looks something like this. It's roughly an exponential profile, like so. And for the holes, it's going to look something like this. So these are the carrier concentration profiles across our junction. Now we'll talk about our diffusion capacitance first, okay? So because we have a forward biased PN junction, there is going to be an accumulation of minority charge carriers on either side of our base emitter junction. So I'm going to call these guys here QDN, and these guys here, Q, D, P. All right. This is because we have these because of the increased probability of diffusion across our reduced barrier potential. All right. These diffusion charge accumulations are dependent on the amount of current that's flowing through the device. So they are dependent on the collector current. And since the collector current is dependent on the voltage VBE, we could say then that these charges are also dependent on the voltage VBE. So for our charge stored on the diffusion charge stored in the base, crap. QDN is simply equal to tau F times our collector current IC, where tau F is what's known as the forward base transit time. And it simply represents the amount of time it takes for an electron to fully diffuse across the base, right? So the electrons are diffusing across the base, then when they reach the collector base junction, they get swept through by the large electric field caused by that reverse bias junction, okay? Since IC is exponentially related to VBE, QDN must also depend on VBE. And from this, we can have a capacitance CDE, which is the derivative of QDN with respect VBE. You guys are in your fields classes right now, so you should know the capacitance is always charge over voltage, right? So this is going to be equal then to the derivative of tau F times IC with respect to VBE, which then gives us simply tau F times GM, since tau F is a constant property. And the derivative of our collector current with respect to our base emitter voltage is by definition the transconductance of our BJT. And so finally, I can write this as tau F times IC over VT. So this is one portion of one of our capacitances. If you'll notice here in our model, CDE doesn't show up anywhere, okay? So the next thing we're going to talk about are our junction or depletion capacitances, all right? And we'll start with our depletion capacitance found at the base emitter junction. So we're going to call that guy CJE, okay? Now CJE, since it is a junction or depletion capacitance, is due entirely to the charge stored within the space charge layer or depletion layer. That is very well defined based on what we know about reverse bias PN junctions from way back at the beginning of ELEN 335. And so we can simply say that it is going to be whatever the unbiased junction capacitance is divided by 1 plus, and we want the reverse bias voltage here, so that would be VEB over the built-in voltage of that junction raised to the coefficient M where M is the grading coefficient of the junction, typically either 1/2 or 1/3, depending on if you have so let's see, I think 1/2 is for step junctions and 1/3 is for linearly graded junctions. I might be backwards on those, but it'll be okay. You'll always just be told what that is. Yes. CJE naught. So let me write that larger. CJE naught. And to be clear here then, this is V naught E. And our grading coefficient is M. All right. So one thing that we need to point out here, okay, this is a forward bias junction. This equation still works, but what should we expect to happen because it's a forward bias junction? We're making the plates of that parallel plate capacitor closer together, right? So we can really approximate this as roughly twice CJE naught for reasonable values of VBE. And by that, I mean we haven't jacked up VBE so much through that we've exceeded V naught E, because that would involve what's called punch through, and you're just burning out your BJT, or you're burning out that PN junction. Okay. Because both CDE are diffusion capacitance for our base emitter junction, and CJE are depletion capacitance for our base emitter junction occur across the base emitter junction, they are effectively in parallel. And so we can say that our capacitance C pi, which occurs between the base and the emitter, is simply those two capacitances added together. So C pi is then simply C DE plus C JE. And depending on where we're operating along this guy's bias curve depends on which one of those two properties are going to be more dominant. We'll talk about that a little bit later. All right, so if we look at our diagram, we have another junction capacitance across our collector base junction. So we should be able to easily see then that C mu, which is the capacitor in our model placed between the base and the collector, is representative of that depletion capacitance. So we are going to have C mu is equal to C J C naught. So the junction capacitance at the collector base interface over 1 plus VCB over V naught C, also raised to the mth power. That takes care of that guy. And then our final capacitance, we can't actually see based on this diagram, so I'm going to draw another quick one real quick. All right, so let's say that we're looking at a cross-sectional view of a silicon substrate over which a BJT has been created. So here we have our emitter. This is our base region. And this is our collector region. Sorry, and this guy should just be N. So we have emitter base and collector, but we must remember that we are on a p-type substrate, meaning that if we have a integrated circuit based BJT, there is also going to be a depletion capacitance seen between the collector and the substrate, which is where that capacitance CCS arises from, where CCS is equal to CJS naught divided by 1 plus VC over V naught S to the nth power. I want to be clear here. So in all of our other junction capacitances, we have a double subscript notation for our voltage in the numerator here. So this is the voltage between the collector and the base. This is the voltage between the base and the emitter, or the emitter and the base, etc. Here, we're only using VC because we are assuming for this NPN transistor that our substrate will be tied to ground. If it were an NPN transistor, our substrate would be tied to VDD, and so we'd need to change that voltage accordingly. But because I've drawn this for an NPN, I'm assuming that this is between the collector terminal voltage and ground, which is where we typically have our substrate tied to. All right, so let's take a minute and do a simple example and calculate the values of these capacitances. So let me write down my problem. Calculate C pi, C mu, and CCS for a BJT operating at IC is equal to 1 milliamp. VBE is equal to 0.775 volts. And VCB is equal to 2 volts. The BJT has the following parameters. So I'm going to say CJE naught, CJC naught, and CJS naught are all equal to 20 femtofarads. Now this configuration where all of these unbiased junction capacitances are equal would actually be, it would never actually happen, right? The reason why this would never actually happen is because the dopant concentration levels are different for each of those junctions, right? So the emitter is the most highly doped region, and the base is the second most highly doped region, which means those parallel plates would be closer together. And so we would see at an unbiased position. And so we would typically see that CJE naught is going to be the largest value. And then since the collector is doped less than the base, we should see that CJC naught would be smaller than CJE naught. And then since our substrate is the most lightly doped, we would see that CJS naught is further smaller. But we are going to see something, even with using these guys as is with an equal value, we'll see something pretty interesting in a moment. For our built-in voltages, let's say that we have V naught E is 0.9 volts, V naught C is 0.5 volts. V naught S is 0.45 volts, I think. Yeah. And then our grading coefficients, MBE, MCB. And MCS are all equal to 1/3. And finally, our forward base transit time is going to be 20 picoseconds. This value typically ranges somewhere between 1 picosecond and 100 picoseconds, because you have to recall from 335 that the actual width of the base is the shortest distance in a PN junction by far. All right, so with these parameters, we can calculate our base emitter diffusion capacitance, CDE, as again simply tau F times IC over VT is going to give us 20 times 10 to the minus 12 seconds times 1 milliamp per 26 millivolts gives us 769.231 femtofarads, or about 0.8 picofarads. Our forward biased base emitter junction capacitance is going to look something like 20 femtofarads times, divided by 1 minus 0.775 over 0.9 to the 1/3 power, because of our grading coefficient, which is going to give us 38.620 femtofarads. So this is pretty dang close to if we had just doubled the unbiased junction capacitance, which is the approximation that I gave you earlier. So we could have saved ourselves a little bit of time by doing that, but isn't particularly difficult to figure out what's going on there. And if we combine these guys, then we have C pi is 807.85 femtofarads. Our capacitance C mu, 20 femtofarads over 1 plus 2 over 0.5 volts to the 1/3 power is equal to 11.696 femtofarads. Who can tell me why I have a minus sign in my CJE and a plus sign in my C mu equation? Right, so effectively the forward biased one is going to have the negative sign, the reverse biased one is going to have the positive sign. But yeah, it's because I was, another way to put it would be because I was given VBE instead of VEB. So I just want to be clear about that. When you forward bias it, you should be making that denominator smaller, which in turn increases the overall capacitance of the junction. When you reverse bias it, you should be making the denominator larger, which is going to decrease the overall junction capacitance. And then finally, we have, let's do it here, CCS. This is another junction capacitance, so it's going to be 20 femtofarads over 1 plus something divided by 0.45 to the 1/3. So we need our base collector, or excuse me, our collector base voltage, right? We look at our equation up here. No, sorry, we need our collector voltage with respect to ground. So how could we get that? Treating our emitter as our reference, the collector voltage with respect to ground is just VCB plus VB, or 2.775 volts. And this is going to give us a value of 10.373 femtofarads. So in general, we can see that C pi is much greater than C mu, which should be greater than our capacitance CCS. And this becomes even more apparent when we don't have the same unbiased junction capacitance values. All right. So we're going to use C pi is much, much greater than C mu periodically. The book does it as well, but the book actually doesn't have any of this crap in there, but I like it. So, all right. So you guys are going to be doing labs on this material shortly, and you'll be probably unhappy to know that none of these parameters are available on a transistor's data sheet. So let's talk about how we can figure out how to get them. And in doing that, we're actually going to wind up introducing a very significant figure of merit for the BJT. All right. So if we look at, well, actually, maybe it'll be better to look at this guy right here. Our collector substrate capacitance, if we had a terminals on an IC that allowed us to directly apply a voltage to our substrate, which we would absolutely have, we could directly measure the capacitance between our collector and our substrate, which is our capacitance CCS. And we could directly measure our capacitance between our base and collector, which is C mu. But because our capacitance C pi depends not only on the depletion capacitance between our emitter and base terminals, but also on the diffusion capacitance when our device is passing current, we're going to have to work around a way to determine that value for a given value of IC, okay? So this is going to seem very unintuitive, but what we are going to wind up doing is creating an equation for beta as a function of frequency, and a consequence of that derivation will actually give us a method by which to calculate C pi, okay? So do any of you guys remember what beta fundamentally is? All right. So beta fundamentally is the short circuit common emitter current gain. So it is simply a relationship between the collector current and the base current, right? So we know, let me just draw a line through this thing real quick. Fundamental definition, beta is IC over IB. Right? All right, so it is the short circuit common emitter current gain. So I'm going to draw a small signal model for a short circuited common emitter amplifier, including our capacitances C pi, C mu, and CCS. And so that's going to look something like this. So here is our base. Here's our resistor R pi. Here is our resistor V pi. Here's our capacitance C pi. Here's our capacitance C mu. Here we have GM V pi. Here we have R naught. I am going to ground my emitter because it's a common emitter amplifier. That seems like a pretty reasonable thing to do, which in turn is going to wind up putting my capacitance CCS in parallel with my resistance R naught. Here's my collector, and then this could be another emitter terminal. So this is my small signal model with my emitter grounded. Hopefully everybody's okay with that, because I haven't really done any change to the small signal model we talked about earlier, except placed CCS, excuse me, in parallel with R naught, and I get to do that when my emitter is at ground. So my emitter is at the same potential as my substrate. This is a short circuit amplifier, so I have to short circuit my output terminal. And so this is going to be my collector current IC, and at my input I'm going to have some base current IB, and beta is simply the ratio of those two currents by definition. So if I call this guy right here node X, and I apply Kirchhoff's current law, I'm going to have some current flowing in through this capacitor C mu. I'm going to have obviously my collector current IC flowing in to node X. Since this guy is short circuited and this guy is short circuited, we should see no current flowing through CCS or R naught. And then I have this guy down, right? So I can say that GM times V pi is equal to my collector current IC plus that current on the left flowing through my capacitance C mu. I'm going to express that as simply this known voltage V pi. So I'll have V pi minus 0 divided by the impedance of this guy, which is going to look like S times C mu times V pi. Everybody okay with that? So the impedance of my capacitor in the frequency domain is 1 over S C mu. So I have voltage divided by 1 over S C mu is the same as voltage multiplied by S C mu. So everybody okay with my math here? I can rearrange this guy, and I will find that my collector current IC is simply GM minus SC mu multiplied by V pi. So now, hopefully it's fairly obvious, I need to figure out a relationship between that voltage V pi and my base current IB. Well, IB, what resistance or what impedance does IB see? So it sees R pi. If it sees R pi, I would argue it sees C pi as well, since they're in parallel. But C mu is also in parallel because we've short circuited our output terminals, right? So we're just going to see that V pi is equal to IB multiplied by the parallel combination of R pi in parallel with the impedance of C pi in parallel with the impedance of C mu. Just Ohm's law. Everybody okay with that? All right. So using Ohm's law, we get V pi is equal to IB times R pi in parallel with 1 over S C pi in parallel with 1 over S C mu, which is going to look like IB divided by 1 over R pi plus S C pi plus S C mu. And from this, I can say that beta, which again is simply the ratio of IC to IB, is going to be this expression, GM minus S C mu. All right, so what have typical transconductance values been for the circuits that we've analyzed? Anybody have any idea? Ballpark it. Pardon? 0.2 watts. 0.2 Siemens. Okay, so somewhere on the order of tens to hundreds of millisiemens, right? Okay, or milliamps per volts, okay? Our capacitance C mu, we scroll back up here, we saw that it's on the order of femtofarads. Arguably, if the true base emitter zero bias junction capacitance were 20 femtofarads, we might see this guy fall into the hundreds of attofarad range. So we have something on the order of 10 to the minus 3 minus our frequency of interest multiplied by something on the order of 10 to the minus 15. So we can say pretty easily that GM, our transconductance, is going to be the dominant term at frequencies lower than the terahertz range, which is well beyond radio frequency and microwave frequency. It's creeping up on optical frequencies. So for the overwhelming majority of applications, we are going to have GM R pi over 1 plus S times C pi plus C mu times R pi, where I've just factored out that, or multiplied both the numerator and denominator by a factor of R pi to get rid of that fraction. GM multiplied by R pi is beta naught, our low frequency value of beta, or how we've been doing it when we've been analyzing circuits. So we're going to say that this is beta naught divided by 1 plus S C pi plus C mu times R pi. So we now have a function of, for beta as a function of frequency. What type of response should we see based on this? Anybody got any thoughts? Anybody remember anything from when we talked about filters in circuits 2 or circuits 3, or when you guys should have done this in 321 last quarter? Anybody this ringing any bells whatsoever? So we have something over 1 plus S times a quantity. That is the response of a low pass filter. If it were S over 1 plus S times a quantity, it would be a high pass filter. So our frequency response is going to look something like this. Here we have the magnitude of beta measured in decibels. Here we have our frequency omega. I'm going to call this guy beta naught. And I'm going to try to construct a Bode plot. So we have a single pole. Let's call this guy omega t. So that's what my Bode plot would look like. Here's my decay of negative 20 decibels per decade because I only have one pole. This guy right here, my pole frequency, I'm going to call omega beta. Can anybody recall how to get the pole frequency from the transfer function? So this is going to be of the form beta over 1 plus S over the pole frequency, right? So from this, our pole frequency, omega B or omega beta, is simply 1 divided by R pi times C pi plus C mu. Now, we're almost done, I promise. This is an amplifier. It's a real amplifier, right? We are measuring the current gain of this amplifier. If this horizontal axis represents 0 decibels, then this frequency, omega t, is what's called the unity gain frequency of our circuit, all right? Since it's an amplifier, we have a constant gained bandwidth product, which means that omega t is simply equal to beta naught, our gain, multiplied by our bandwidth, which is omega beta, right? Our pole frequency here, or our minus 3 dB frequency, they are one and the same, represents the bandwidth of this low pass filter. So I can multiply the bandwidth of the low pass filter by the gain of my circuit, and I get the gain bandwidth product, which must equal to 1, which is by definition my unity gain frequency, okay? So I can manipulate this a little bit. Beta divided by R pi is just going to give me GM divided by C pi plus C mu. And since we know that C pi is much greater than C mu, we have simply then transconductance divided by C pi, which gives us a method of determining the value of C pi based on our operating point, right? Because GM is simply IC over VT. Expressed as a linear frequency, we can say that FT, which is what's called the transition frequency or transit frequency, is then simply GM divided by 2 pi times C pi plus C mu, or approximately GM over 2 pi C pi. All right. So this transit frequency is actually a very important frequency because this tells us how quickly our transistor can operate as a switch. So this is the intrinsic fastest frequency that our transistor can perform at in a digital circuit, which is a very important thing to know. If you were trying to design a microcontroller or something like that using BJT technologies, this is the limit. This is how fast it can perform operations. The more complex and more stuff we add to this circuit, the lower that frequency is going to become, okay? On a data sheet, we might see a graph that looks something like this. So we won't just see the transmission frequency, or excuse me, transition frequency by itself. It'll be plotted as a function of IC, which makes sense since it depends on the transconductance. And so that graph would look something like this. Here's IC in milliamps. And in this region here, where it's relatively flat, so when FT is approximately constant, C pi is approximately equal to CDE, and we know that C pi is much greater than C mu, giving us C pi is tau f times GM is equal to IC over 2 pi FT VT. So we can actually figure out what our transit frequency, our forward base transit frequency is as well, if it weren't given to us, by knowing what C pi is and looking at this graph. Okay, so let's see, we have 15 minutes left. All right, I'm going to skip that example problem. We're going to move to Mosfets. All right, so our high frequency model for Mosfets. Is going to look something like this guy. We have a gate. We have some capacitance CGS. Hopefully that makes sense to everybody since we've always talked about the gate to source as a parallel plate capacitor. One that may not be as intuitively obvious, we're going to have a capacitance CGD. Here's our dependent current source that converts some voltage at the input, VGS, to current at the output. Here we have GMB, VSB. I don't know whether Dr. Batari talked to you guys about the body effect or not, but I talked to my students about the body effect in 335. 99.99% of the time, that current source is going to be ignored. So you can just pretend like it isn't there if you don't know what the hell I'm talking about when I mention the body effect. Here we have our channel length modulation resistance R naught. We are going to have some source body capacitance, CSB, where this is my voltage VBS, and sorry, this should be VBS because this is a ostensibly an NMOS I apologize for that. We are going to have a capacitance between the drain and the body. So here's our drain terminal. Here is CDB. These guys get tied together. Here's my body terminal. Here is my source terminal. So this ugly looking thing is our high frequency MOSFET transistor model. Now, if we tie our source and our body together, which is what is done in the textbook that we are currently using, the overwhelming majority of the time, this will simplify to the following. Here's our gate. CGS survives. CGD survives. GM, VGS. We are for sure not going to have any body effect. CDB, yeah, sorry, I'm trying to figure out why I drew a capital B there because I shouldn't have. Here is our drain. And so here's something where legitimately I'm a smidge confused, okay? In the textbook that you guys are using, it explicitly draws a source to body capacitance even when the body effect is ignored. But that capacitance is shorted out, so I don't know why it's there. And in literally every single example problem, they say it doesn't matter because it's shorted out. So I'm going to draw it because the textbook has it in there, knowing full well it's going to be neglected literally every time we see it, okay? So just want to be real clear about this. So this is our source. This is our body connection. And we will have CSB. So drain, CD. I think in the textbook, this is then called CDS. But anyway, all right. I might have to change the subscript on that guy later. Not a big deal. Okay, so let's talk about where the hell these guys come from, because I think we have enough time to do that. So I'm going to draw a cross section of a MOSFET. So here is our source. Here is our drain. I'm going to draw this in orange. So this is just a metal one layer. We're also going to have a metal one layer providing our body connection. We have our channel. And in saturation, it's going to look something like that, right? We have hot pink. Actually, let me do this in gray. This is our gate oxide. Then we have our poly electrode, which is our gate. And this is a P-type substrate. All right, so a couple of things I want to point out here. There is an overlap. So the gate overlaps the source and the drain. This is due to, well, it's really one reason, but it's two effects, okay? So in a self-aligned gate technology, which means we're using a polysilicon gate as opposed to a deposited metal gate or something like that, the gate acts as a mask for when you are actually implanting the source and the drain. When the substrate is annealed, which is a heating up process, that causes the source and drain to diffuse out a little bit, meaning that the gate will always slightly overlap the source and always slightly overlap the drain, which is why modern transistor technology has the yield that it does. Back in the day, when the source and the drain were established and then the gate was put on, roughly only 70% of transistors were actually able to work due to misalignment errors. The self-aligned gate process causes this to go down. It's roughly 99% of transistors should actually be able to work. But it does result in a region of overlap like so, which is in turn going to cause an increase in the capacitance as we see. So we are going to see a capacitance between our gate and our channel. We are going to see a capacitance between our gate and our source where there's that little bit of overlap. We're going to see a capacitance between our gate and our drain where there's that overlap. We are also going to see a capacitance between our source and our body connection because that is a reverse biased PN junction. And we are going to see a capacitance between our drain and our substrate because again, we have a PN junction, right? That's typically going to be reverse bias, meaning the drain potential is going to be much higher than the substrate potential because the substrate potential B is usually tied to 0 or ground. So with that in mind, our total gate source capacitance, CGS, is a combination of our channel capacitance. So when we have this, if we didn't have pinch off, this would simply be the width of the transistor times the length of the transistor times the oxide capacitance, C-ox. But because we have this no longer parallel plate because of pinch off, we're going to call this 2/3 WL C-ox, representing our channel capacitance. And then we also have that overlap capacitance, which is going to be WL overlap times C-ox. So this takes care of this guy and this guy. Okay, so that's our gate source capacitance. Just for your reference, L overlap is usually somewhere around 0.05 to 0.1 of the transistor length. So it can be fairly appreciable. All right. Our gate drain capacitance, CGD, is equal to an overlap capacitance. So we don't see any capacitance in our channel because it's pinched off. So we don't have any, there's a lot of charge over here, There's next to no charge over here, so we don't see any capacitance due to the channel. All we see is that overlap capacitance. And so we just have WLOV times Cox. For our source body capacitance, this is a depletion layer capacitance between the PN junction formed by the source and the substrate. So this should be CSB naught divided by the square root of 1 plus VSB over V naught, the built-in voltage of that junction. That looks like terrible. You may be asking yourself, why in a Mosfet is it square root instead of that thing multiplied or raised to the power of m? It's because the way that Mosfets are built is consistent. It's always a step junction. So we always have that. So literally the way it's fabricated forces that particular grading coefficient to be there for all of our reverse bias junctions. Then we have our drain body capacitance, CDB, which is going to be CDB naught divided by the square root of 1 plus VDB over V naught. This is the exact same built-in voltage for both of these junctions because the source and the drain in a MOSFET transistor are interchangeable. They are both doped at the same dopant concentration, and they are both sitting in the same substrate, so they have to have the same built-in voltage. So we only have to deal with the one of them. And so this gives us all four of our capacitances that we see in our model. We have 5 minutes left. All right, so I have an example problem. We're not going to work it. Instead, we're going to jump ahead to the transition frequency of MOSFETs. I might just post all of my notes so that you can see my example problems and all that kind of stuff. So we can develop a relationship for the short circuit current gain in a MOSFET as well. So with the source and body tied to the same potential, that's going to look like this. Here is our gate. Here's the source and body connection. This is CGS, making this VGS. This is CGD. Here's GM VGS. Here's R naught. Here's CDB. Here's our drain. We're going to ground our source and body. So this is the source and body connection as well. Going to do the exact same thing. So we're going to find a short circuit relationship. So this is, we'll call it I out. And this guy is I in, making sure I got everything labeled. Looks like I do. Let's call this guy node X. Applying KCL at node X, just like we did for our BJT, gives us SCGD times VGS. That's the current flowing from the input to node X, plus I out, that's the current flowing in from the right, is equal to GM VGS, which we can rewrite as I out is equal to GM minus SCGD VGS. Using Ohm's law, VGS is IN divided by S times CGS plus CGD. So IN sees our gate source capacitance in parallel with our gate drain capacitance. And so the voltage drop is just that current multiplied by those two impedances in parallel, right? And from this, our short circuit current gain is then I out divided by I in is GM minus SCGD divided by SCGS plus CGD, which will be GM over SCGS plus CGD for the majority of frequencies of interest for the exact same reason. Now, transconductance for Mosfet was typically a little bit lower than that of a BJT. So we're talking about single digit to tens of milliamps per volt. Maybe actually we might see hundreds of microamps per volt. Our capacitances here will be on the order of single digit to 1 to 10 femtofarads. So again, as long as we're not operating at terahertz frequencies or hundreds of gigahertz really, then this approximation should hold. So the magnitude of our current gain here will be equal to 1 when S is equal to GM over CGS plus CGD, right? So that means that our transition frequency omega t is equal to GM over S CGS plus CGD, which is going to be sorry, there shouldn't be an S there because we are finding out the value of S that makes that thing 1. I apologize for that. CGS plus CGD, which is approximately GM over CGS. And our linear transit frequency is then GM over, I'm trying to do this so fast, I'm making dumb mistakes. 2 pi times CGS plus CGD, or GM over 2 pi CGS. Our transit frequency is again representative of the maximum switching speed that our transistor can have. So this tells us, this is a helpful comparison if we're comparing different transistor technologies or different generations within the same transistor technology. So this is ultimately how fast a transistor can operate, which means how useful it might be in a circuit requiring high frequency operation like computers, microcontrollers, etc. Again, I have another example problem, but we don't have time to do it because class ends in 1 minute. So yeah, that's enough out of me for today. So we have laid the groundwork for our frequency analysis now. We have our high frequency models. We understand what the Miller effect is and how we can use that. We are going to definitely introduce what's called the method of short circuit time constants on Wednesday, because there's going to be some times when the Miller effect isn't applicable and the circuit looks terrifying and we need to get just a quick and dirty estimate instead of suffering through tons and tons of math to figure out what's going on. So that's enough out of me. See you guys on Wednesday, because today is totally Monday. Will I be in my office hours today? Yes, I should be, Evan.